Dear students, welcome in the CEC Gurukul lectures. We are dealing with the characterization of nanomaterials, and in this part we are characterizing the optical properties of the nanomaterial by using the spectroscopic method. In the today's lecture we are discussing the Raman spectroscopy. As we discussed in the previous lecture that Raman scattering takes place at the frequency other than that of the incident frequency. It may be increased or it may be decreased. So when it is decreased, then it is a stock line. When it is increased, then it is a anti-stock line. So here we see that on the diagram we are seeing that there is a graph between the intensity versus frequency. We see that the stock lines having the lower energy state and the anti-stock line having the higher energy state. At the high energy state, frequency here in the stock is less, and in the frequency is more in the anti-stock line as compared to the incident frequency. In this diagram we are seeing that at the middle one we are having the Rayleigh scattering. The middle peak, which is of a higher peak, it means the more light of the same intensity will emerge out, more light of the same intensity will emerge out, as in the Rayleigh scattering no change in the energy. But here in the left hand side in the stock line you see that there is a change in the frequency. The graph peak is less, but here in the right hand side the frequency or the energy change in the anti-stock line. So this is the basic scattering phenomena, Raman scattering phenomena and the Rayleigh scattering. Now in the stock and anti-stock lines we are having the wavelength. We can deal with the wavelength also. The radiations can be characterized by using the wavelength. In the spectroscopy, as we are interested in the interaction of the radiation with the various energy levels of the molecules, which may be examined at the various terms of the energy. Means, as we are again saying that sometimes we are saying energy, frequency, wavelength, so we can characterize it with the various parameters. Like we can use the frequency, we can use a wave number also, and we can relate it with the energy, as all are convertible. So in characterization we can take the graph between the frequency and energy, can the graph between the wave number and the intensity and energy and the, so in this manner we can take these words. Now, what is the Raman scattering process? What is the process behind the scattering? Now, here we see in the diagram that here this is the basic process. Light from the laser fall upon a mirror, which is apart from the natural density filters. Most of the filters were used to get the fine light, and then after mirror the light will focused by the lenses, then it fall upon a sample. From the sample it pass from the camera lens, then again we are having a filter, then we are having the polychromator, that is the detector, and the last CCC detector used. Then the display we can get on the computer. As is the schematic diagram of the Raman process. We see here the most of the important components are laser, which is a source, mirror, which transmit the light, will give the position of the light, focus lenses, which focus the light, sample cell. This is very important to hold the sample. What type of sample we can use? Liquid, gas, or solid sample we can have, and that we can put in the sample cell. After that it pass from the camera lens, and then after camera lens again the filter is used, detector is placed there, then the computer, which is the display unit. So what are the basic components of the scattering? Are the laser, scattering cell, detector, and the computer. But what is the process? The Raman scattering arises when a photon is incident on a molecules and interact with the electric dipole polarizability of the molecules. As we know that the laser light is fall, means photon is interacting with the molecule of the sample, then there will be the change in the electric dipole. It is a form of electronic spectroscopy, although the spectrum contains a vibrational frequency, as there is a change in the there is a change in the vibronic state. Vibronic means vibrational plus electronic state. So it is one of the electronic spectroscopy, while the spectrum which we are getting only from the vibrational frequency or the vibrational level. In the classical term, the interaction can be viewed as a perturbation of the molecule electric field. As the photon of a particular intensity fall upon a material, then the electric field will change, means there is a change in the electric field. In the quantum mechanics, the scattering is described as a excitation to a virtual state lower in the energy than a real electronic transition, with nearly coincident de-exciting and the change in a vibrational energy. As if we talk about the quantum mechanics, the molecule or the atoms will jump from the lower state to the higher virtual state by gaining the photon. The scattering event occur within a 10 to 14 second or in the less time. Thus the virtual state description of the scattering works. It means scattering takes place by using the virtual level. So in the Raman scattering process, we are having the vibrational levels and the upper virtual level, where we can get the scattering of the molecules, gaining and the loss of the energy. The next part is the instrumentation of the Raman spectroscopy, or what are the most important parts in the Raman spectrophotometer. Here see, this is the schematic diagram of the Raman system or the Raman spectrophotometer, where we are using a left hand side, we are seeing that laser source, then we are having a sample cell, then wavelength selector. It means we take the output we take the particular wavelength output by using the filter. Then radiation transducer, which passes the radiation to the that works as a detector also. Last is the computer, which is a display unit that contains the data, that contains all the record and the output or the Raman spectrum. Here what are the main components in the Raman systems? Source of monochromatic radiation, that is the laser source. Second is the sample compartment and associated which associated with the optics. Sample compartment means it may be of the quartz or the silicon glass. So the sample holder may be of the quartz is very important. That is also called a sample illumination system, where we put the sample in a qubit. Then we are having the spectrometer or the monochromator that will be used to filter the light, and that is a suitable spectrometer we required. After that, a detection system, which may be the diode, and then we are having the display unit, or you can say it is a computer. So these are the main components of the Raman system: source, sample holder, spectrometer, detection system, and the display unit. Now what is a source? As again we repeat that we use a monochromatic source. So monochromatic means having the single radiation, and the laser is the best choice for this. So laser is used as a source in the Raman spectrophotometer. The source used in the modern Raman spectroscopy are nearly always lasers, because their high intensity is necessary to produce a Raman scattering of the sufficient intensity that can be easily measurable for the signal to noise ratio. Because of the intensity of the Raman scattering, which vary from the fourth power of the frequency, we can use the organ krypton ion source that emits the blue and the green light, which is in the region of the UV, and the spectrum have the advantages over the other sources also. Now here we see that the source, the various green and blue sources we can use for the Raman scattering. Laser are used as a photon sources due to their high monochromatic nature and the high beam fluxes, and helium neon laser, which emits the highly monochromatic light of the wavelength 632.8 nanometer. Moreover, the helium neon laser is a commonly used excitation source in the modern Raman spectrophotometers. Other examples are argon ion, which is having the wavelength of 488 nanometer or the 514 nanometer. Krypton, that may be tuned krypton ion, that is the 530.9 to 647.1. Helium neon diode, that is having the wavelength 785 to 830, that may be in the range of the red line, sometimes we required. Then Nd:YAG, it depends upon the material which we are characterizing. Nd:YAG, that is of the wavelength 1064 nanometer, which is in the infrared region. So this is the sample illumination system. What type of the sample we can use? We can use the liquid, solid, gas. What is the liquid samples? A major disadvantage of the sample handling in the Raman spectroscopy compared with the infrared arises because of the water is a weak Raman spectra. Here it is very clear in this liquid sample we use the water, because it is having a very weak Raman spectra, apart from the IR spectroscopy where we use the different solvents, but in the Raman spectra we can use the water also. Thus the aqueous solution can be studied by the Raman spectroscopy but not in the infrared spectroscopy. The advantage is a particular important of the biological and the inorganic system and the study dealing with the water pollution problems that can be characterized by this Raman spectroscopy. Solid samples we can use. Raman spectra of the solid samples are often acquired filling of the small cavity with the sample after it is ground at a, it is just like a grain, or it is just like a powder that can be used as a solid sample to characterize by using the Raman spectroscopy. Polymers can also be used directly, as polymer film can be put directly on the can be directly put in the sample holder, and then we can characterize it. There is no special sample pre-processing in the Raman spectra. Gas samples. Gas are normally contained in the glass tubes that of 1.2 centimeter in the diameter and about 1 mm thickness. Gases can also be selected in a small capillary tube, and that will be put in the sample holder, and that can be characterized for the Raman scattering. Then samples, you see in the diagram that this is a sample holder where we can put the sample for the characterization. In the Raman spectrophotometer or the Raman spectrometer, samples may be examined as a solid liquid solution and in the gas phases. Raman spectra is the most easily obtained by using the liquid samples. Most of the time liquid samples are used, and they are, if they are dissolvable in the water, then it will be more better. Then Raman spectrometers, which is the third part of the Raman component. Raman spectrometers is similar in the design as that of the classical ultraviolet UV visible instrumentation we have discussed. It is quite similar to that of UV visible spectrophotometer. Most employ double grating system to minimizing the as we are seeing here that we are getting the fine scattered light. So this is very important to use the double grating or the many gratings, so that the sharp peak or the sharp radiation or less noise ratio will reach up to the transducers. The multipliers served as a transducer, means the detector must be off, must be getting the fine output because of the fine output by using the double grating. So photomultipliers gain the output light from the sample that produce the Raman scattering. Here you see in the scheme of the Raman spectroscopy, we are having the various components as we already discussed, that light source, then inelastic scattering takes place, then it will go through the filter to the photomultiplier tube, then the spectrum will be recorded on the computer screen, and here we see the sample of the Raman spectra. The Raman shift we will getting in the spectra. So this is the scheme of the Raman spectrophotometer. The Raman spectrophotometer, we use the good intensity, as we are using the laser light, so that the atoms can be excited at the virtual level. It was explained that the intensity of the Raman line is much weaker than the exciting line. The incident line having the more intensity, but the emergent scattering light having the less intensity. So it is a great challenge to capture the scattered light with the low intensity. So spectrophotometer required the good photomultipliers tube. So one of the great challenge in the Raman spectrometer to remove the Rayleigh signal, as it is having the more intensity as compared to the scattered other Raman scattering light. This is accomplished in the old spectrometers by using the very large double or triple monochromators with the large focal lengths of the 1 meter and the very high resolution. But nowadays we are using a filters. So last before coming on the display unit, there is a detector. The most commonly used detector is the photomultiplier tube, which provides an excellent sensitivity, produce the low noise ratio, signal will be higher, and a large dynamic range we will get. The screen we are seeing the detector that is used in the Raman spectrophotometer. The detector may be multi-channel detector, which is having a dimensional diode array, and the pixels of order of 512 or the 1024 of the two-dimensional type of the Vidicon or the charge coupled devices we can use as a detector. So these are the photomultiplier or the multi-channel detectors we can use. There are the various type of detector: single channel detectors, which are photomultiplier tube, photodiode, array detector, which are photographic emulsion, photodiode arrays, and non-silicon array detectors are also there. So these types of detectors are used in the Raman spectrophotometer to detect the signals which is very less which is having the very less intensity as compared to the incident light. So last but not the least is the display unit, which is the computer nowadays, which is incorporated in the modern instruments, are essential for the manipulation, for the addition, extraction, and self deconvolution, and moreover, this is also contains the record of all the samples, predefined dictionary available in the storage. So they are indispensable when a multi-channel detector is being used, and often a major advantage is with a single channel system. Good software and graphics facilities for the Raman spectroscopy for developing a analytical tool. This is the output which we get on the screen, and this is the one of the here we are seeing the various peak which define the change in the wave number. Here it is represented by the wave number and the intensity. Intensity is also varying, wave number is also changing with a particular ammonium permanganate material we are using, and that will define the Raman spectrum, the graph between the intensity versus wave number, and how this wave number is changing as at of the various points. Now, what is the difference between the Raman and the infrared spectroscopy? This Raman spectroscopy is different from the infrared spectroscopy. In the infrared spectroscopy, we are dealing with the absorption, but here in the Raman spectroscopy, we are dealing with the scattering. That's why it is called a Raman scattering spectroscopy, and that is infrared absorption spectroscopy. Then what are the difference between the Raman and the infrared spectroscopy? In the Raman, it is due to the scattering of a light by a vibrating molecules. But here in the infrared spectroscopy, absorption of light by the vibrating molecules. And the second point, the vibration is Raman active if it causes the change in the polarizability. But here in the IR, vibration is IR active if there is a change in the dipole moment. In the Raman, we are having the polarizability, but here in the infrared, we are having the dipole change. Next, in the Raman, molecule need not process the permanent dipole moment, but here in the infrared spectroscopy, there must be a change in the dipole moment because of the vibration. Water is used as a solvent in the Raman, but water cannot be used in the IR spectroscopy because it is having the intense absorption of the IR infrared radiations. In the Raman, the sample preparation is not very elaborated, as we can use the direct state of the matter, but here in the infrared, sample preparation elaborate the gaseous samples can rarely be used. Means in the Raman we can get the spectrum of the gas sample, but here in the infrared region we were not able to get the gaseous sample. The Raman gives the gives the indication of the covalent character in the molecules, but this infrared gives the indication of the ionic character of the molecule. This gives the covalent, this gives the ionic. Type of Raman spectroscopy. There are the various type of Raman spectroscopy. As the resonance Raman spectroscopy, that is called the RSS. Second is the surface enhanced Raman spectroscopy, that is SERS. Then micro Raman spectroscopy, and nowadays we deal with the non-linear Raman spectroscopy techniques. So these are the various types of Raman spectroscopy to characterize the material. So we will discuss in a brief about all the different Raman spectroscopy. In the Raman resonance spectroscopy, the UV lasers allowed for the better Raman performances. Here we use Raman. In this Raman resonance, the ultraviolet range lasers we will use because of the 1 by lambda power 4 dependence of the scattering, but fluorescence is a problem in this type of Raman resonance scattering. But there is a difference between the Raman and the fluorescence, as in the Raman we are using the virtual upper level, but fluorescence this type of we are not dealing. And with the laser in the 245 to 266 nanometer region, the Raman spectrum can be fit in this region above the laser, but below the normal stock shifted fluorescence spectra. If it is okay in 245 to 260 nanometer, but apart from this, that will gives the stock shifted the fluorescence spectrum. So next is the surface enhanced Raman spectroscopy, which is the one form of the Raman spectroscopy that involves a molecule absorbed to the surface of the nanostructure metal surface, which can be supported by the local surface plasma resonance excitation. So this surface enhanced Raman spectroscopy dealing with only the surface of the molecule. The Raman scattering intensity depends on the product of the polarizability of the molecules and the intensity of the incident beam. That's why LSPR amplifies the beam intensity when the beam is resonance with the plasmon energy level leads to the signal enhancement greater than that of the 10 power 6. So in this surface enhanced Raman spectroscopy, we use the local surface plasmon resonance for the excitation. Next is the micro Raman spectroscopy. As the name suggests, micro, where we deal with the micromolecules. That is the powerful technique for analyzing both a live cells also and scaffold materials used in the tissue engineering. So micro Raman spectroscopy, we can get the spectrum of the atoms, molecules of the material, the sample of the micro size. A Raman spectrum is produced following the interaction of the exciting laser photon with the vibrating molecule in the sample. The process will be the same. Next is a non-linear Raman spectroscopic techniques. Non-linear, why we are dealing with that? Pre-laser era, we are dealing with the conventional light sources, but after the discovery of the laser, we are dealing with the non-linear optics. In the non-linear optics, the Raman defined as the non-linear Raman scattering, and that technique is known as the non-linear Raman spectroscopic techniques. In the non-linear Raman spectroscopy that based upon the non-linear effects, where we are dealing with the change in the susceptibility of the material that will be increased with the increase of the intensity of the light or with the increase of the energy. So in the non-linear Raman spectroscopy, we deal with the Raman active molecular transitions. This non-linear Raman spectroscopy divided into three parts. First is the stimulated Raman spectroscopy, second is the hyper Raman spectroscopy, and third is the coherent anti-stock Raman scattering. These three different Raman scattering, basically here we are changing the frequency of the light with the there is a various parameters of changing the frequency of the incident light after scattering. So what are the applications of the Raman spectroscopy? There are the various application in the field of chemistry, physics, and other branch of the sciences. The Raman spectroscopy is commonly used in the chemistry, since vibrational information is specific to the chemical bond and the symmetry of the molecules we can find. So it provides the fingerprints by which the molecules can be identified. Second important, in the solid state physics, it is used to characterize the material. You can measure the temperature and find the crystallographic orientation of the sample. Raman spectroscopy can be observed other low frequency excitation of the solid, such as plasmon, magnon, and the superconducting gap excitation. And other Raman spectroscopy can be used to investigate the chemical composition of the historical documents, such as continued knowledge, social economic conditions, and time of the documents were produced. Raman spectroscopy is being investigated the explosive for the air security. And Raman spectroscopy can be used to find out the various minerals in the sample or in the compound. It is used in the medicine, aiming to develop of the new therapeutic drugs and the diagnosis of the various diseases. And in the inorganic species, it is used for investigating the aqueous solutions in the composition. And basically it is dealing with the vibrational energy. Then metal ligands bonds are generally in the range of 100 to 700 centimeter inverse. So in this reason the infrared is very difficult. Infrared spectroscopy cannot work, so we use the Raman spectroscopy. And there are the various Raman potential useful for the information regarding the composition, structures, and the stability of the coordination compound in a molecule. In the organic species, the Raman, the infrared, in that there are reasons that useful for the functional group detection and the fingerprint reason that permits the identification of the specific compound. Raman spectra yield more information about certain type of organic compounds than that of the infrared spectroscopy. There are the other various methods but the Raman spectroscopy is used for the gaseous, solid, powder and various samples. Water is used in it. Inorganic, organic and biological materials can be used to characterize. Pure chemical mixture and solution in general it is not suitable. Analysis of the metal and the alloys. Typical examples where the Raman is used today include various carbon material structure and the purity of the nanotubes detection. We can find out the defects in the carbon nanotubes and other tubes. Disorderness can be characterized by using the Raman spectroscopy. In the chemistry, structure, purity, reactions monitoring we can do. In the geology, we can use the mineral identification, distribution, fluid composition and the phase transitions we can find out. And now finally these are the various references where we got the presentation. Thank you very much.